We now consider the expansion of the gas between states A and B using a very large number n of steps. On this slide, n is equal to 41. It is easy to see that as the number of steps becomes very large, the magnitude of the work, as represented by the area in red, becomes indistinguishable from the area under the isotherm. The two would actually be identical if the number of stages for the expansion between A and B was infinite. This situation corresponds to the case where the gas is expanded infinitely slowly, so as to preserve the equilibrium between the gas and its surroundings at all times during the expansion. This corresponds as expected to the case where during the expansion the gas pressure P and the external pressure P sub external are approximately equal to each other at all times. As shown by the isotherm P equals nRT divided by V, as the expansion proceeds and the gas volume increases, the gas pressure, hence the external pressure, decreases systematically from an initial value of P sub A to the final value of P sub B. The expression of the work was written in the preceding slides as minus the integral from VA to VB of P external times dV. The near equality between P external and P, the gas pressure, means that we can write the work as minus the integral of P times dV. Since the gas considered here is ideal, we can replace the pressure P, which is changing during the process, by nRT over V. The reason for doing so is that to integrate the product P dV, we need an expression of P as a function of V. Since we also considered here that the temperature was kept constant during the expansion, we conclude that the term nRT is a constant, and as such, can be taken in front of the integral sign. So the work can simply be calculated as minus nRT times the integral of dV over V. This well-known integral yields the natural logarithm of V between VA and VB. Hence, our final expression for the work of isothermal expansion of an ideal gas carried out using a very large number of infinitesimal steps, that is, carried out very slowly, is W equals minus nRT times the natural logarithm of V sub B divided by V sub A. Such an expansion is called reversible or quasi-static, because under these conditions, the gas pressure is approximately equal to the external pressure during the whole process. Had we done similar calculation for 1-step, 2-step, 3-step, 4-step, and many-step isothermal compressions of an ideal gas, we would have found that the magnitude of the work is largest for the 1-step compression and is lowest for the compression carried out with many infinitesimal steps. We would also have found that the magnitude of the work of expansion from VA to VB is identical to that of the work of compression from VB to VA, only when the compression is carried out infinitely slowly. This is why when expansions and compressions of substances are carried out infinitely slowly, these processes are said to be reversible.